Take it away, Pedro. Thank you.
Okay, thank you, Carmen. Thank you very much to the organization for inviting me. It's a pleasure for me to be here celebrating the Louis Kaufman birthday. I'm going to speak about a new torsion pattern in Khovanov homology. As far as we know, is the first torsion pattern useful for non-semi-adequate links. And a nice thing is that it appears in quantum degree other than penultimate and antepenultimate degrees. This is a joint work with Raquel Diaz. And then in next talk, Raquel will extend and amplify some result on the same topic. Okay, I will divide the talk in three parts. First, I will introduce carefully the Khovanov homology from using the Pedro's approach. Then I will summarize some results about torsion. The papers I am going to cite have been the main motivation for our study of this topic. And in a third part, I will introduce a new torsion pattern. This torsion pattern must be seen in the A smoothing of the diagram. We will identify an element that defines distortion, and we will sketch the proof that is a torsion element. Then we will show some examples. Let's start with the Khovanov homology. Let L be an oriented link, and D an oriented diagram of L. Its crossings arbitrarily ordered. A Kaufman state is a map from the set of crossing of the diagram into a set of two labels, let's say A and B, usually also 0 and 1. SD is the union of circles obtained smoothing D according to the state. And when we do the surgery, we left a small core. We call it scar after the surgery. This scar is blue if the label is A, red if B. The number of circles of SD will be denoted this way. And we have also, in addition, to enhance the state. This is done by assigning minus or plus to each circle of SD. Each enhanced state has two different degrees. An homological degree I, which is simply the number of B labels, and a quantum degree J equal to I plus tau, where tau is the difference between the number of circles plus and the number of circles minus in SD. We are going to define a chain complex, so the modules are Cij of D. This will be the free abelian group with basis the set of enhanced states of D, with homological degree I and quantum degree J. Let's see an example. Here we have a state with 1 B label, so I is equal to 1. We have, this is the result of the smoothing, and we have assigned minus to both circles. So tau would be -2, and then J, which is the sum of I and 2, is equal to -1. So in this case, this enhanced state is a generator of C1 -1D, right? Now we are going to define the differential, and we need to define first what is the meaning of the expression S prime is derived from S. S prime and S are both enhanced states. We say that S prime is derived from S if labels assigned by S and S prime are identical, except in one crossing. We call it a chain crossing. And in that crossing, S assigns an A label, S prime a B label. In particular, I of S prime is I of S plus 1. The signs of the common circle of D and S prime D must be identical, and the quantum degree must be equal. So as I increases by 1, we need tau to decrease by 1 in order to keep the quantum degree. What happens is that the uncommon circle of D and S prime D are those touching the chain crossing. Passing from SD to S prime D can be realized by merging two circles into one, or splitting one circle into two. And remember that tau must decrease by 1. So the possibility for the signs of this circle this one, plus goes to plus minus to minus, minus plus to minus. But minus goes to 0 because it's the only way that tau can decrease by 1. And for a splitting, we have plus to plus minus or minus plus, and minus goes to minus minus. Then we can define the differential. First, C of D is just the sum of all this module, and the differential D increases the homological degree by 1 and preserves the quantum degree. So Ij goes to I plus 1j. It is defined as the differential of state S is a linear combination of state S prime, where the coefficient S prime, we call it the incidence number of S over S prime. This number is defined as minus 1 to the k if S prime is derived from S and both states have KB labels among the crossing prior to the chain crossing. If S prime is not derived from S, this coefficient is just 0. Okay? So in here appear only S prime when S prime is derived from S. And in such case, this coefficient is minus 1 to the k, where k is the number of labels among the crossing prior to the chain crossing. D squared is equal to 0. And then for each integer j, we have a chain complex. And this defines a Khovanov homology of the diagram, which is the kernel of di quotiented by di minus 1. J is fixed. And the whole cohomology is the sum of all this cohomology. We keep an underlying referring always to the diagram D, Khovanov homology of diagram D. This is not a link invariant. We need to shift the indices. Shifting the indices, we make it independent of the diagram. And we obtain the Khovanov homology of the oriented link. Here, by definition, this is the homology of the diagram. And the shifting is I is equal to H plus M, and J is equal to Q minus P plus 2M. Here, P is the number of positive crossing of the diagram, D, and N is the number of negative one. Khovanov homology is an invariant of not unlinked. This means that in this calculation does not depend on the diagram D chosen for representing the link L. Here we have an example, the Khovanov homology of knot 5,2. Rows are indexed by quantum degree, columns by homological degree. For example, we have here a torsion in 3 different quantum degrees. Khovanov homology was developed by Mikhail Khovanov at the end of last century. It categorizes the Jones polynomial. The coefficient of t to the q is an alternative sum of the rank where h runs the homological degrees. It's a stronger invariant than Jones polynomial. For example, these do not have the same Jones polynomial, but different Khovanov homology. Moroka, Akronheimer proved that Khovanov detects them not. We still don't know if Jones polynomial does it. The invariant defined by Rasmussen via Khovanov homology provides a lower bound for the slight genus. This bound was used by Pizzirillo in order to prove that the Conway knot is not a slice. Now I will survey some results about torsion. I start with a conjecture by Shumakovich. Khovanov homology of every non-split link except the trivial knot, the Hopf link, or a connected sum of Hopf links has torsion elements of order 2. Note that if these were true, then we had another proof of the fact that Khovanov homology detects the knot. Lee proved that split alternating links are H-thin and there is no torsion in the upper diagonals. Recall that H-thin means that the Khovanov homology concentrate in 2 consecutive diagonals. Asaida and Pritiki proved that this link, other than the Shumakovich exception, have 2 torsion. Paviniak, Pritiki, and Satanovich in several papers have also addressed the problem of existence of torsion in semi-adequate links. With González Meneses, Silvero, and myself, we proved that the string Khovanov homology of a link is the cohomology of a certain simplicial complex. This theorem allowed us to construct knots with as many non-trivial modules in the string homology as desired, providing examples of arbitrary H-thick knots. However, none of these examples contain torsion in the string quantum degree. Pritiki and Silvero have conjectured that this simplicial complex is in fact homotopy equivalent to a wedge of sphere, and in particular does not contain torsion. We have proved it for some large classes of samples, but the conjecture is still open. Torsion of the higher than 2 appears rarely. Among all prime knots up to 16 crossing, all alternating ones have only 2 torsion. Only a few have 4 torsion. For some time, it was conjectured that 3 torsion never appears, but Barnatan showed that the torus knot with 20 crossing, T56, has it. I do not know if there exists a link with less than 20 crossing and 3 torsion. I know that the cluster of this braid with at most 20 crossing has 3 torsion. This is a very optimistic conjecture by Shumakovich as well. The Khovanov homology of a knot is determined by its torsion part. Maybe very optimistic. For example, these 2 knots have the same free part, but different torsion. Many other papers have this problem. Just say that Mukherjee has shown a sample that disproves and conjecture by Pritiki and Satanovi relating torsion and braid index. However, one conjecture is still open, believed to be true. The Khovanov homology of a link obtained as the cluster of a braid with 3 strands has only 2 torsion. Cluster of 3 braids has only 2 torsion. Shumakovich has proved that thin links have only 2 torsion. Chandler, Lawrence, Satanovich, Summer have proved a local version of the result, providing more evidence for supporting the above conjecture. What about recognizing a specific torsion element? We have two very nice results by Aside and Pretiki. Let it be an A-adequate diagram. This means that the A smoothing, in the A smoothing, any scar has its two string into different circles. Suppose that the A smoothing has a cycle of odd length. Then there is torsion in the penultimate quantum degree. For example, in here we have the A smoothing with a cycle of length 5. Then there is torsion and the element defined, but just one enhanced state with one B label and every circle made. With similar hypothesis, if you have a cycle of even length with a single edge, then the torsion appears in the antepenultimate quantum degree. These are really elegant results, but they are restricted to semi-adequate links. And the torsion they determine can appear, is confined to the penultimate or antepenultimate rows of the homology table. We will present now our new torsion pattern. Is useful for a large class of nodes, not only for semi-adequate link, appear not only in the penultimate or antepenultimate quantum degrees. We start with a definition. This is a diagram of type TGH. If we look at its A smoothing and see one main circle, G parallel monochord outside, H parallel monochord inside, nothing in between. In addition, we can have extra circle or extra because. We say that this is a monocircular diagram of type DGH if in addition the A smoothing has no extra circle. So monocircular diagram of type DGH are really just the standard diagram of the pressure link with G -1 and a tower of H positive crossing, something like this. If G is equal to 2, then we have a tower with H positive crossing, and here a clasp. And what appears is just the mirror image of a twist knot. Now we will see the main result of this talk. Let it be a diagram of type DGH, and let GD be the graph that starts with the A smoothing, delete the monochords, and take a vertex for each circle. So this is the graph GD. Well, assuming that this is a diagram of type DGH, if GD is bipartite, R is a node integer less than H, then we have two torsion. And in fact, the torsion appear in indexes I equal to R plus 1 and J to R minus the number of circles in the A smooth. And another nice thing of this result, I think, is the fact that the torsion element can be explicitly described. The chain B that define the two torsion is a sum of G times H over R enhanced states. The idea for understanding this state can be seen with an example. Here we have just G equal to 2 monochords outside, 5 monochords inside. We have added here some extra circle. The graph, note that the graph is bipartite. Here we have 5 monochords inside, so we can take R equal to 1 or R equal to 3. R must be, recall, must be odd and less than H. For example, if we take R equal to 3, appear state of this type, 2, 4, 5 indicates the red scars. This 2 is for the second outside, 2, 4, 5 inside. And what about the enhancement? Well, first, this is SD. Note that this red scar split the main circle into a tower of small circles, R+1 circles, but the outside red scar merges the two extreme circles into one. Then the sign where the central circles here are plus, external circles are all of them minus, and the merged circle is minus as well. This is indicated by this 0 here, the merged circle with a minus in the notation. This is the definition of the element V, which is going to define the torsion, the two torsion. Note that in total we have R+1 B labels, and J is equal to 2R minus the number of circles in the smoothing. And before giving a proof sketch, I will show some example. Here it is the trefoil and diagram of tie, monocircular diagram, in fact, of tie 2, 2. Two monocircular, two mono edge outside and 2 inside. Then we can take R equal to 1, and the chain B is just the sum of 4 states with one red scar outside, one inside, and with sign minus in the only circle. Note that with one red, this circle splits into 2, and with the other red, merge back. So we have only one circle. The torsion appears in coefficient, in indices to 1 for the diagram, and in the knots is in coefficient -2, -7. From this to this, you have to know that this diagram has 0 crossing, 0 positive crossing and 4 negative crossing. Then this homology can be seen in the table of Khovanov table of trefoil, given the only torsion that appear in this knot. Another example is the Borromean link. We can consider this nice diagram. The corresponding A smoothing is of type 2-2. In here, appear 2 external circles, but the diagram is bipartite. So we have torsion in the Borromean link. Now I'm going to present an example that can be used for constructing infinite families of knots and links that have this pattern. For example, start with knot 819. Consider it's a smoothing, note that is bipartite. Add 4 monocores, given our pattern. From this, we recover the knot. Here, there are 4 crossing coming from these 4 monocore. As a P rotation, produce, delete 1 crossing and produce the mirror image of a non-alternating knot with 11 crossing. This has 2 torsion as well. And this procedure can be used in many contexts, and adding here, for example, different number of monocores. Another example, 5-2, we consider the arm with one crossing, one more crossing. The a smoothing is of type 2-4. This is the Khovanov table. We detect two copies of torsion, one for R equal to 1. Recall that this blue is I, and recall that I is equal to R plus 1. So for R equal to 1, we have this torsion. For I equal to 3, this torsion. And the nice thing here is to know that this torsion appear not restricted to the penultimate or antepenultimate quantum degrees. Another examples will show that the hypothesis R less than H is necessary. Here we have a diagram which is 2 of type D to 5. So H is 5, and if we take R equal to 5, so I is equal to 6. There is no torsion in this column, so this hypothesis is necessary. Well, I will sketch the proof. The complete proof is long and quite technical, so I will concentrate just in monocircular diagram. In general, what we need is we have V in this module, and we need to define a chain in this module satisfying the following condition. The differential of X is V plus V, and V is not exact. That means it's not in the image of the differential. These two conditions, of course, tell us that V is defining a two torsion element. So we have to define this element X that, recall, has R B labels. V has R plus 1 B labels, but X must have R B labels. The general definition of X is a sum of states in which we consider R B scar inside. Here in this definition, lambda index the set of external circles, and L alpha is the length of any path from the corresponding external circle to the main one. Since our graph is bipartite, these numbers does not depend on the chosen path. So that's where we use the hypothesis of the graph being bipartite. Let's see how these states are. In the sample where we have 2 monochord outside, 5 inside. Again, we take R3, red scar inside, for example, 2, 4, 5. And we are going to see all the different enhancements. Note that here, because we have a red scar here, this red scar split the main circle into a tower of circle. If you have R B labels or red scar, you have R plus 1 circle. So this is circle 0, 1, 2, R. And the sign where the central R plus, and you have to add a minus in the rest of the circle. You can, a plus. You can put it in the circle 0, in the circle R, or in the different circle external circle, which are this one, alpha. Remember that lambda index the set of external circles. And here appears an alternative sum, recall. This is the definition of X. Well, now we, as I said before, the general proof is long and needs a careful comparison test. So we will concentrate on the monocircular case, which is the idea, at least for the monocircular case. In that case, there's no external circle, and X is just the sum. And here 2 examples. recall that the central circle were plus, and there was another plus in the rest of the circle. So in this case, it is better to identify the enhancement indicating the only circle with a minus. So this is just R minus. Instead of 0 plus, I say R minus. And this is, instead of R plus, I say 0 minus. And X is written this way. So X is written this way. Here are the typical enhanced states representing this element. And now recall that the differential of a chain consists in differentiating the different crossing. In each crossing, I should substitute a label for a B label. I will refer to outer crossing, and J will refer to inner crossing, right? So the key observation is that if I differentiate this with a crossing outside, I must to convert one of these blue scar into red. Then there is a merging of the two circles, and minus plus goes to minus. And that happens if you have here minus plus or you have plus minus. This happens in these two situations. So in both cases, we have merging minus plus to minus or plus minus to minus. It follows that the differential effect is to V, since B, recall, was the sum of these enhanced states, plus a sum of something that I call W, and it is the differential of this sum, but with crossing inside. J corresponds to blue scars here. It's important to note that in W is a linear combination of a state of this form. Here we have our red label, now appear R plus 1, and also appear two minus, two circle minus. One will have 1, and if, for example, you turn this blue scar into red, this plus goes to plus minus or minus plus, so another minus appear. So we have two minus here. But at least one of these circle is 0 or the last one, or R plus 1/3. So let's examine the coefficient, for example, if one minus is in 0 and the other is in the middle. Then we integrate this state and obtain two possibilities. If LK was blue, and then the only circle minus is this one, or LK plus 1 was blue. These are the two possibilities. The only two possibility that when differentiated, you get a minus in this circle K. Well, then the corresponding incident number, you can see that are the same except for a sign. Why? Because this has K-1 B labels or B scar before, but this has K, the K-1 plus this one. So the signs are different, so the coefficient of the state is 0. Similar arguments show that the coefficient of this is 0, and in the case in which the sign minus is in the two-string circle, the only non-zero incident number involved are this one. In here, I have this L1 turned into blue. So this is the differential of this is this one, or this is sustained by integrating this one. In this one is R plus L R plus 1, which is blue. And here I have incident number equal to 1, and here I have -1 to the R, because there are B scar before. So if R is O, this coefficient cancel, W is 0, and then the differential of X is equal to B. So it remains to prove that B is not exact. For it, let M be a submodule of CD generated by a set of enhanced state, a set M, with homological degree I and quantum degree J. We consider this composition. Here D is the differential. Pi is just the projection onto the module M, or Gothic M. Epsilon is the map that sends each enhanced state to 1. It's an augmentation map. I would like to note that this composition was already used by Thomas Kindred, in order to find non-trivial homology classes in Khovanov homology. Now, if R is greater than 1, consider this set of enhanced states, this particular set. What happened then is, on one hand, epsilon composed with pi applied to V is just 1. This happened because in this module, the only summand of V is when you have here K equal to 0, which is this summand. So this gives you 1. But on the other hand, if you apply this to any differential of any chain, you are going to get something which is into R. R is the ring. In our case, you can think that was the integer number, so we are getting some even values. This is 1. These are even values, so B cannot be the differential of anything. So B is not exact. The same case, in the case in which R is equal to 1, this set generating the module is not valid, and we have to consider a different module. Just a remark about this theorem. The idea this is more than a question than a statement. The above theorem suggests a possible relation, at least under certain condition, between the torsion of a node, which is the boundary of a plumbing of two surfaces, and the Khovanov homology of the boundary of both surfaces. Here is one asterisk S2 is the plumbing of S1 and S2. Let's see why I say that. Consider this plumbing of these two surfaces. This surface, the boundary of this surface is this pretzel node, which is a monocircular diagram. We know that it has torsion. And in the proof, the part we haven't done, we are adding external circle in a bipartite graph. This is something like considering this primitive flat surface, doing the plumbing of these two surfaces. And what we know is that this surface contains two torsion. We knew that the boundary of S1 had two torsion, and after this plumbing, we know that the boundary has two torsion. So one guess if there is some general result of this type for plumbing and torsion defined by other different elements. Just a last example to finish. Here it is the Khovanov homology of the node 7,2. We have 3 torsion detected by our pattern. Here 4 are equal to 1, are 3, are 5, but there are still 2 torsion that are not recognized by our pattern. In next talk, Raquel will explain how to recognize those torsion. In order to compare what Raquel is going to say with I have said here, in the result presented here, we have dealt with 2 ladders of blue blue steps. This is a ladder, this is another ladder, joined in a very specific way. Here, a torsion element has been defined, roughly speaking, by taking 1 red step outside and an odd number inside, less than 8. In next talk, Raquel will consider a situation that allow more than 2 ladders, and under certain conditions, a torsion element will be defined by taking at least 2 red steps in each ladder, and an odd number greater or equal than 3 red steps in one of them. In any case, the result in both talks are independent. The proof in this talk are maybe more technical. Well, that's all. Thank you very much for your attention.
Let's thank Pedro for his talk.